Okay, in this video we're going to take a look at applications of inequalities. So let's do that with a couple of examples. And our first example, we're going to have someone standing at the top of a cliff, throwing a ball way up high in the air, and then it falling down into the water. So something like this. And they take their ball and they throw it up into the air, and gravity takes over and it plunges down into the water. And as you can see, that looks a little bit like a parabola, the way that it travels up and then back down over time. And so I'm going to model that with a height equation, the height at time t, and I'll give you that. It's negative 16t squared, negative, it's going down, it's a quadratic, and then plus 40t plus 20. So for instance, you know the height of the cliff actually is 20, because at time 0, when they have it in their hand, these are both 0, and so the height would have to be 20 at time 0. We could do interesting things like find out when does it hit the water and make a little splash, and that would be when the height is equal to 0, and then we'd have to solve this little quadratic. But I'm actually not going to ask either of those questions. Instead, I'm going to ask, for how long was this ball higher than 25 meters? So somewhere up here is the 25 meter mark. I want to know for how much time did it spend above that? And this is basically an inequality. So I want to know when was at what times was the height, so this piece here is going to be 25, and I want to know when the height that my ball got to is greater than or equal to 25. So this minus 16t squared plus 40t plus 20 is the height that my ball is at any time, and I want the height that the ball is at any time to be higher than 25, and that'll let me know the time span when it is above 25 meters. Well, just like I did in previous sections, I'm going to take this inequality and I'm going to simply make it an equality so that I can go ahead and solve it, and that'll allow me to find out these two times. And I'm going to assume there's two, one when the ball goes up, one when the ball comes down, and I should get two solutions, both being positive times for when how many seconds after 0 it hits to go up. It should be pretty quick, and then when it comes back down. So to solve this, I simply make it equal to 0 by subtracting 25 on both sides, and I could go ahead and use the quadratic equation since it's probably easier than factoring this, so I'll do that. So t equals, it's negative b plus or minus b squared minus 4, a is minus 16, and c is minus 5, and divided by 2a's. And I'll need a calculator to do some of this. I get negative 40 plus or minus the square root of 1280, so there will be two solutions, and then negative 32, and let's just get the decimal places. I'll really number crunch here for you. And I get 0.13 and 2.37 seconds. So almost immediately after I throw it, about a tenth of a second after I throw it, it hits that 25 meter mark, and it stays above that until almost 2.5 seconds. And of course, how long was the ball above that is the difference between these. So on my calculator, I actually stored these as A and B, and so the difference is B minus A, and I just type that in on my calculator, and I get the actual time is rounded to two decimal places, 2.24 seconds. It was above 25 meters for about 2.24 seconds. And I'm just finding the difference. Okay, let's take a look at another example. Okay, a hotel charges $200 a night for a single room and $300 a night for a double room, and a team books some rooms there, but they book no more than 10 rooms. There's no way that they need more rooms than that, or the hotel doesn't allow them to book more than 10 rooms, and the total amount of money that they're allowed to spend has to be no more than $1,800, so less than or equal to $1,800. So I want to write a system of equations to model this scenario, and I want to somehow describe the possible room bookings and costs. Okay, well, I've got some hotel rooms at $200 a night. I'll call those maybe X. So let X be the number of single rooms. And I've got these double rooms. That's different. So let Y be the number of double rooms. And now I can come up with some equations. If I take the number of single rooms and add the number of double rooms, I can't get any bigger than 10. And actually, you can't get any smaller than 0 either. So the x plus y together has to be bigger than or equal to 0. Kind of seems like a strange thing to say, but you're not going to go book any negative rooms. And then the total amount of money that I spend, well, for each room that's a single, I have to spend $200 and $300 for each room that's a double, and that total has to be less than $1,800. And technically, I'm not going to go and give them my money, so the 200x and the 300y, I have to spend some money. I can't spend negative, so it's got to be greater than or equal to 0 as well. So there's some of these ones that are kind of obvious in the scenario that we're dealing with. So there's a system of equations to model this scenario. Let's take a look and see what that might look like graphically. So I'll just move this down a bit. So x plus y is less than or equal to 10. X plus y equals 10 would be y equals negative x plus 10. And if I graphed that, I would have a y-intercept of 10, which I'll put, say, here, and a slope of negative 1, and it would go down this way to here. That would be 10 as well. And I have to now test which side of this am I on. So x plus y less than or equal to 10. Test the point 0, 0, or test the point even 1, 1. 1 plus 1 is less than, so I'm definitely in this sort of zone. Let me just rescale this quickly, and I get a graph that probably looks something a little bit more like this. Now I have to do the other part of this inequality, and I'll do that in red. So I've got 200x and 300y would be equal to 1,800. And so let's solve for y. 300y would equal negative 200x plus 1,800. Divide by 300 would give me negative 2/3 x plus 6. So if I start at 6, I would have a slope of negative 2/3, and so I would go down 2 and over 3, and down 2 and over 3, and down 2 and over 3, and I would get to 9. So I'd actually have a graph here like this, and again, I have to test a point, so let's test 1, 1, and 1 and 1. 500 is less than 1,800, and so that's good. I have my zone inside a zone. Actually looks like this. That's at 9. And so now the combinations that I could go and book are represented by this space. So I could actually book no rooms. I could just cancel, and no rooms of, these are the singles on this side, and these are the doubles on this side, because that's what I defined as x and y. So no rooms at all would be totally fine. I could book at most 9 single rooms. That would be $1,800. That would be under 10. I could book at most 6 this way. That would be 6 times 300. And I can book any combination. So 5, 4, 3, 2, 1, all the way across this way, and all of the points inside here that run right along this line are inside here. Now, technically, I can only book integer points. So to shade in the whole thing is actually a little bit wrong. It should just be a bunch of dots across here. So interesting little thing. These should just be the integers inside this zone. We're not going to get that particular about this, but the constraint on money is more of a constraint to this problem than the constraint on the rooms, because the hotel will let me book more rooms. It's solutions that are out in here, but I don't have the money for some reason to be able to book them. Okay, we'll get some practice with this in class. See you then.